All right. Good day, everyone. Welcome to this exciting episode of our YouTube lessons. We are going to be diving into the chemistry of the quantum today. We're going to look at the things not in this world. So it's called the quantum realm. If you have watched Ant-Man, you heard of the quantum mania, the quantum realm. So we're going to be looking at the quantum realm and how the concept came about. So what is quantum? Now, actually, quantum actually is a is a word is used to is a term used for substances that are not in the atomic level. So substances that are subatomic, that are in the electron proton level. They are so small. They are referred to as quantum. So that terminology is referred to the quantum. So when you hear of quantum realm, it means a realm that is so small below the atom. If you ask what is an atom, check other videos. An atom is the smallest particle of an element that may or may not exist on its own, but take part in a chemical reaction. We are going to be looking at atom. We looked at atom earlier. We're going to look at every atom as we know it. Um, Usually have a tiny core, which is the nucleus, and electrons moving around them. Whenever you see like a planet circularly, where electrons are moving around. So these electrons are in a realm we call the quantum. Yes, quantum. So now, according to Schrodinger, um, de Broglie and Werner Heisenberg, these electrons moving around this nucleus is like a wave. It's like a wave, and it's difficult to actually know the position or location according to Heisenberg. Now, so modern theories have looked at what we call quantum numbers to be able, or have assigned electrons quantum numbers to be able to easily locate them and denote how many or quantify them in the atom. Yes, so these electrons include these quantum numbers given to these electrons to be able to quantify them and qualitatively analyze them count them for an atom. These numbers or these quantum numbers are of four types. So these quantum numbers are of four types. So it makes the wave mechanism model of an atom efficient. If you don't know what the wave mechanism is, then check out subsequent videos. We're looking at the models of an atom, the basic history of the atom. So the quantum numbers are numbers used to locate the electron basically. Now, this video will be very useful to you when we know the four types of quantum numbers. The types of quantum numbers are principal quantum number. Let's take note. We have the principal quantum number. Okay, we have the azimuthal quantum number. So we're going to apply them videos and how they come out in exams such as A-level exam, IGSCE exam for the UK, some foreign exams and some basic higher level institution exam. So the other type of quantum number we have is the magnetic quantum number. It tells us the magnetic orientation. We're going to look at that now. Then I'm going to look at lastly the spin quantum number. The spin quantum number. Yes, the spin quantum number. Okay, so spin quantum number. So the principal quantum number has a value of n. The spin quantum azimuthal quantum number has a value of n. The magnetic quantum number has a value of mn. Then spin quantum number has a symbol of ms. So these are represent this symbol. So when you see n is equal to, that's the principal quantum number. Usually for atoms, you see for this atom, this electron has n equal to this. I'm going to dive into that in this video. So I'm going to start with the principal quantum number very fast. Now, the principal quantum number, how it works and the way it will work. Now, the principal quantum number tells us the energy level. So, take note of the things it tells us. It tells us the energy level of every electron. So, or what we traditionally say, it tells us the type of shell that every electron belongs to. So, each of these electrons are in levels called energy levels, or we call them shell. So the principal quantum number tells us which shell they will belong to, which orbit are they going to belong to. So the shells basically are K, L, M, N. What are their value of N? Their value of N is 1, 2, 3, 4. Now, some will say O. Now, O, we have a value of 5. Yes, we have a value of 5. Those are their value of N. Those are their values for N. So, first, we all know that this shell is going to be the K shell. This shell is going to be the L shell. If there's another shell, it will be the M shell. If there's another shell, it will be the N shell. So, this place, N is equal to 1. First orbit. Now, another thing the principal quantum number tells me, the principal quantum number tells me the size of the orbit. Size of the orbit. Tells us the size of the orbit. And it will also tell us the size of the orbitals. I'll come again and talk about orbitals. Talk about orbitals. I'll talk about orbitals. It tells us the size of the orbit and the size of the orbital. It is denoted with the symbol M. It is denoted with the symbol M. That's the principal quantum number for you. So that is for the quantum numbers. Per se, that's for the quantum numbers. Tells me the shell, the size of the orbit, the energy level that each electrons are going to belong to. So that is the principal quantum number N. So now we will dive into the next one, the azimuthal quantum number. So when we get to the azimuthal quantum number, it becomes more interesting. It becomes more interesting. Now let's go for azimuthal. For azimuthal quantum number. Okay. For azimuthal quantum number. Now this one represents the subshell. Now, one thing you should take note of, the symbol for the azimuthal quantum number is L. Yes, it's actually small letter L. So, now for the azimuthal quantum number, it denotes the subshell. It denotes every subshell. Okay. Now, and the subshells are usually represented with S, P, D, F, G. So, their value for L is going to be 0, 1, 2, 3, 4. Yes, these are the values for L that we have 0, 1, 2, 3. Having said that it denotes subshells, these are the values for L, which we already said before. And one thing should be noted that azimuthal quantum number is also known as subsidiary quantum number. Subsidiary quantum number. Now, or angular momentum quantum number. That means from the azimuthal quantum number, we can calculate the angular momentum of an electrons according to Neil Bohr. Yeah, the angular momentum of an electron moving on in an orbit according to Neil Bohr from the azimuthal quantum number. The quantum number should be noted. Quantum number was not discovered by a scientist, and it was talked about. It was used by Max Planck in his quantized energy theory, by Albert Einstein, by Schrödinger, by Neil Bohr. Even Neil Bohr used quantum numbers to explain one of the more prominent equation, which is the NVRO, to calculate the angular momentum. NVRO is equals to nh over 2 pi. One of his equation in his theory. N there stands for the principal quantum number. So Neil Bohr already used quantum numbers to explain. So they are just numbers. I'll call them hypothetical numbers given to electrons. Now let me quickly say something. Now for azimuthal quantum number, from there I can get the shape of the orbitals. The shape of the orbital. So normal, the subshell S is spherical in shape. So the orbital of S we have a spherical shape. So S we have spherical shape. P we have dumbbell shape. Spherical in shape. P is dumbbell. D is double dumbbell. D is double dumbbell in shape. F is complex. F is complex. So these are the shape of the various orbitals, and these are their shape. Now, taking this off, please let me put them here. So I'm going to put them here because we're going to apply now. G, what's the value for L? 0, 1, 2, 3, 4. Now, for every value of N, for every value of n is a principal quantum number, there are n values of L. What is L? Azimuthal quantum number. So what I'm saying, for any value of a principal quantum number, there are that same value of the azimuthal quantum number. What do I mean? When n is equals to 5, it means that the number of azimuthal quantum number that I should have when n is equals to 5, or break it down, the number of subshell I should have when n is equals to 5 is 5. How do we normally get it? When n is equals to 5, the values of L are possibly 0, 1, 2, 3, and 4. It should be noted that n can never be equal to L for an electron. So for an electron, the principal quantum number and the azimuthal quantum number are not the same thing, sir. Okay, so for n values of a principal quantum number of n, there are n values of L. So I come again. Let's try another example. Now let's say our L is equal to 3. Use simple one. N is equal to 3 means KLM, M shell. What are the subshells possible there? L would therefore be equals to 0. From 0 to 2 will not get up to 3 because N cannot be equals to L. 0, 1, 2. That's it. So what is 0, 1, 2? So the possible subshell here are going to be the S, P, and D. So for the third shell, there's nothing like F subshell. So it should be noted. Yes, it should be noted. So also, I can also get a formula from this. Now, for a given value of n, we as scientists in modern day theory, we've been able to find out that the number of electrons, though this was not among the quantum theory, the number of electrons for a value of n is equal to 2n squared. Yeah, very simple. So number of electrons is equals to 2n squared. So what do we mean? We mean that when n is equal to 3, for instance, let's see how many possible electrons can it take. So remember, n 2, 3 squared. So 3 squared is 9 times 2, that's 18. So you can take 18 electrons. So there are 18 electrons when n is equal to 3 in the third shell. So the maximum number of electrons that can stay in the M shell is 18 electrons. Okay, now what about the number of orbitals for a value of n? So for a value of n, number of orbitals are regions in the subshell where you can find electrons. Orbitals are regions in the subshell where you can find electrons. Yes, region in the subshells where there are no possibility of finding an electron. Yes, it occurs. Those regions are called the forbidden region for the atom. So a forbidden region is a region in the atom where there's no possibility of finding an electron. So in between the forbidden region and the orbital, there's what we call a nodal plane. There's a plane there, a nodal plane. So please, this is for number of orbitals. So they can ask you, for a value of n equal to 3, how many orbitals can we have? How many orbitals? They can also ask you how many shells. When n is equal to 3, how many subshell can we have? The subshell we can have is L. So for n equals to a value, there are n number of that value. For n equals to a value, there are n number of L values. So when n is equals to 3, it means that there are 3 values of L. When n is equals to 4, there are 4 values of L. What does L stand for? Basically, subshells. Subshells, that's what it stands for, subshells. The meter value number stand for subshell. So they can ask you how many subshells are in n equal to 3. Number of subshells equals to n equals to 3 are 3 subshells. What are the subshells? L, which is 0, 1, 2. S, P, D. But what are the number of orbitals? I can get it from this. Though, when I have the values of L, I can get the orbitals. But this is like a short way out. So to get the values of orbital, number of orbitals you can have, just simply n squared. N squared, this is a short way out that you can also use. So let's say 3. How many orbitals can I have? So 3 squared should be how many? That's 9 orbitals. So n equals to 3, I have a total of 9 orbitals in that shell. That 9 orbital cut across S subshell, P subshell, and D subshells. I can calculate. In secondary school, they told me S has 1 orbital, P has 3 orbital. 1 plus 3, that's 4. D has 5 orbitals. So 1 plus 3 plus 5, that's 9 orbitals. I'm putting in my shortcut. So azimuthal quantum number should not be an issue. And always note that n is never equal to L. N is never equal to L. So we know this one. Now, quickly, for values of L, there are also some short formulas you can also give you. Please take note of these ones because I'm taking it off soon. You can pause the video and take them down. Okay, now taking note of this one, please. Taking note of this one. For number of electrons for given value of L, we can use 4L plus 2 in case you are just in the exam or you are in a rush. How many electrons can a a shell or a subshell with quantum number of L equals to 3 contain? L equal to 3 or L equals to 2. L is equal to 3. How many electrons can it take? So you just use this formula. Simple as that. Now, how many orbitals can it take? The number of orbitals it can take is 2L plus 1. This is a short way out. This is a short way out. A short way out. So this is a short way out. So I've said everything concerning the azimuthal quantum number. It shows me the angular momentum, the shape of the orbitals. Yes, and it denotes, azimuthal quantum number denotes subshells. It denotes subshell. That means every value of an azimuthal quantum number, every value of L represents a subshell. Now, I'll quickly say something. Now, for instance, when you're writing electronic configuration, write 1s2. Now, I'll quickly say something. This one stands for the principal quantum number, while this S stands for the azimuthal quantum number. Please take note. This one stands for the principal quantum number. This L stands for the azimuthal quantum number. So the principal quantum number here is 1. N is 1 for 1. A 1s2 electron. N is 1. L is going to be 0 because X, the value of S, the value of L for S is 0. Now, let's quickly look at the magnetic quantum number and how it tells me the orbital orientation and, if possible, the magnetic orientation, because the orientation of every metal, or the magnetic orientation of every metal is depending on the type of orbitals and the type of electrons on the orbital. So magnetic quantum number is represented with ML. So it is a symbol of ML. Some will say M, simple capital letter M. No, it tells us the orbital orientation. Yes, it tells us the orbital orientation. Orbital orientation. Yes, it tells us the orbital orientation. The orbital orientation. Yes. Now, since it tells us the orbital orientation, now magnetic quantum number ML is derived from the azimuthal quantum number. So magnetic quantum number ML can just be given as minus L to plus L. These are the values. So let's say L is equal to 2. When L is equal to 2, if you watch earlier, that is standing for the D subshell. So for the D subshell, how many orbitals are going to be there? How many orbitals tell us how many values? So it's going to be minus L to plus L. So the magnetic quantum number for L is equal to 2. D subshell is going to be minus 2 to plus 2. So minus 2, minus 1, 0, plus 1, and plus 2. So how many values are you seeing? There are 5 values. How many values are you seeing? 5 values. It tells me that L equal to 2, which is a D subshell, have 5 orbitals oriented in this manner. So these are the values of each of the orbital. So the first orbital has a value of minus 2, second orbital has a value of minus 1, third orbital has a value of 0, fourth orbital has a value of plus 1, the last orbital has a value of plus 2. These are the values of the orbitals. Now, when you feed electrons into these orbitals, when the electrons are singly filled, it tends the atom is tend to be, especially atoms that have singly filled electrons, especially on their valence shell, um, singly filled electrons on their orbitals, tend to be paramagnetic, while the ones that have electrons that are paired, so that are not singly filled, that are paired, are said to be have very low magnetic field, very low magnetic field. So they are said to be diamagnetic. They are said to be diamagnetic. So, so singly field is representing paramagnetism. Now, highly paramagnetic substances are ferromagnetic. Now, to also be paramagnetic means it stands for many things. One of which is the for paramagnetic substance, the magnetic field of the substance is greater than the applied magnetic field. That's what it means to be paramagnetic. You're partially magnetic. To be diamagnetic, you are not magnetic. It means that your magnetic field is less than the applied field on you. So that means you don't have a magnetic field. You don't have unpaired electrons. That's also we see that transition metals have a lot of unpaired electrons. They are paramagnetic. Highly paramagnetic substances are ferromagnetic. Example of ferromagnetic atoms: iron, cobalt, nickel. Okay, so that's for azimuthal quantum number. So azimuthal quantum number is this simple. It tells me orbital orientation, the magnetic orientation, how I can fit electrons into orbitals. And fitting electrons into orbitals, I have some rules you follow. There's some basic rules you use. The last quantum number we're going to look at is the spin quantum number. The spin quantum number. So that shows us the direction of the electron in every orbital. Direction of the electron in every orbital. So spin quantum number. Spin quantum. Spin quantum number. So let's look at spin quantum number. What does spin quantum number tells me? Spin quantum number tells me or shows me um, the direction of the electrons. Now, the possible spin we can have in an atom is represented as ms are two possible directions, especially of electrons in orbitals. Clockwise direction and anti-clockwise direction. That means every electron around the nucleus goes in two directions, to the left, which is anti-clockwise, or to the right, which is clockwise. And no two electrons can have the same spin, especially two electrons in an orbital. The maximum number of electrons in an orbital is two, and none of those electrons in an orbital can have the same spin. If one is plus half, the other is a minus half. Yes, minus half. So that's spin quantum number. It tells me direction. So I can quickly treat some questions on this topic. Now, treat some questions. So I'll treat one or two questions. So I was going to look at example one. Example one. For example one, I want to ask example one. How many how many electrons how many electrons are in how many electrons are in a 5G? Yes. How many electrons are in or will be in a 5 or in a 5G subshell? So I'm going to quickly try this one. So using my formula, a very short formula, for number of electrons in a subshell, look at the formula, is 4l plus 2. Another way is to calculate the number of orbitals that are in G, which we get 9 orbitals from the value of, see one way if I use this formula method, SPDFG. The value of L is 0, 1, 2, 3, 4. So 4. Yes, 4. So L is 4. So magnetic tells me orbital orientation. So magnetic, I'm going to have minus 4 to plus 4. So how many orbitals? Minus 4, minus 3, minus 2, 1, minus 1, 0, 1, 2, 3, 4. So I'm going to have 9 orbitals. 1, 2, 3, 4, 5. So this is minus 1, pardon, minus 1. I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, 9 orbitals. So there are 9 orbitals in a G subshell. So in a G subshell, there are 9 orbitals. Every orbital takes 2 electrons. How many electrons are there? 18 using this. Now, but if we are not to use this to save time in the example, just put the formula 4 plus 2. So what's the value of L for G? It's 4. So it's going to be 4 into 4 plus 2. So what should I have? 4 times 4 is 16 plus 2. I have 18 electrons. It is quite simple. Quite simple. So I'll try another one. I'll try another one. Now see this one. Okay, try another one. Um, okay. So I'll try another one. Okay. What are the values? What are the values, example 2, of N, L, M, L, and S? Now it should be noted that spin quantum number can also be represented as S. N, L, M, L, and S for a 4f4 electron. So for a 4f4 electron, what are the possible values of N, L, M? Now I told you earlier, because it's 4f, the value of N is the coefficient 4. L is F. Now for SPDF, what are the values of L? 0, 1, 2, 3. So F is 3, L is 3, which is correct. How do you know you are correct? N should not be equals to L. What about ML, magnetic? Now, for the 4f4 electron, there's a particular electron. Now, F, it should be noted that F contains 7 orbitals. There are 7 orbitals in F, 7 orbitals in F. Okay, 7 orbitals in F. And I would not like to do that now. Just watch the video backwards. You see how to get it. 1, 2, 3, 4, 5, 6, 7. So if I'm to feed the electrons, I'm 4 electrons. This is first one, second one, third one, the fourth electron. The fourth electron has a value. That's the value. So this is ml. So ml is going to be minus L. So the value of ml, magnetic orbital range, is going to be minus 3 to plus 3, minus L to plus L. So minus 3 is the first one to plus 3. Minus 3 is the first orbital, minus 2, minus 1, 0, 1, 2, 3. So it means that the 4f4 electron is, when you ask you for 4f4 electron, it means you need the fourth electron. That the fourth electron on this orbit has a magnetic quantum number of 0. Why is it 0? I come again. Why is it 0? I come again. First, you get the orbital orientation, ml, minus 3 to plus 3, minus L to plus L, minus L to plus L. So minus 3 to plus 3. If it is minus 3 to plus 3, if it is minus 3 to plus 3, each of the orbitals have a value, minus 3, minus 2. When on the fourth orbital, where the fourth electron will be, the number will be 0 for magnetic quantum number. Remember, magnetic tells us orbital orientation, so magnetic will be 0 for a 4f4 electron. Then what will be the spin? The spin quantum number, there are two possible spins, but that's a spin up. So we can just use plus half. Some other tests can use minus half, also correct. So these are the values of the 4 quantum numbers of a 4f4 electrons. Of a 4f4 electrons. So we'll take the last example before we go. The last example before we